All right, we're doing 7.4.3, Algebra 1, exponential and linear growth. All right, so we've covered arithmetic sequences, we covered geometric sequences, and then we did kind of took like an interest in bacteria, and then as well as Fibonacci and pyramidal sequences in the last section. So let's jump right into it. No time to waste. All right, so use the table to answer questions 1 and 2. Is the function represented in the table linear? All right, so they're giving x values 1, 2, 3, 4 now. The x values are just your terms. They determine the order of the sequence. So this is the first term, second term, third term, fourth term. What we actually care about are the y's. The y values are our values. So we will do, all right, so going from 105 minus 103 is 2. 107 minus 105 is 2. 109 minus 107 is 2. They all have a consistent common difference, right? It's all the same number added or subtracted. So that would be arithmetic sequence, which is equal to linear. So yes, it is linear because it's arithmetic. And how do I know? Because the y values have a common difference, right? It's the same number is being added each and every time. And what would the fifth term be? Well, I just add. 109 plus 2 is 111. Done. All right, so we have to use this table for question 3 and 4. Is it exponential, which would be geometric? So I see it says exponential. I'm thinking geometric. So what I'm going to do is I'm going to do 21 divided by 7 is 3. So this is times 3. 63 divided by 21 is going to be 3. 189 divided by 63 is going to be 3. See, these are all being multiplied by 3, so yes, it is geometric. And how do I know? Because it has a consistent common ratio. The same number is being multiplied each time. So what would the fourth term of the sequence be? Well, I'm going to, the fifth term of the sequence. I'm going to take the fourth term, 189, and I'm going to multiply it by 3. All right, so I just multiply the fourth term by 3, and that will give me 567. Alright, it's kind of ugly, but it's fun. Alright, so I just took 189 multiplied by 3, which is my common ratio. Use the table to answer questions 5 and 6. Is the function represented the table linear or exponential? Well, let's try. I'll do 9 minus 14 is equal to negative 5. I'll do 4 minus 9 is equal to negative 5. Negative 1 minus 4 is negative 5. So I got a consistent common difference. That means it's going to be linear. And why? Because it has a common difference and not a common ratio. What is the recursive formula? So we have to go back to the first, so 7.1 to get the recursive formula of our arithmetic sequence. You should have this either written down or memorized. Probably written down. Have it written down for your test. Have your study guides ready and available to you. It's going to be boom. So all I need to, this is my recursive formula for arithmetic sequence. So all I need to add to this is the common difference. So I subtract 5. All right, that's it. That's the recursive formula because that's how to get that common difference. Where did I get the common difference from? From doing subtraction within the chart. All right. Now, is this function represented in the table linear or exponential? All right, let's look. I would need to do 2 minus 2 fifths, and then 10. It ain't gonna work. All right, so then the subtraction is just not gonna work. 2 divided by 2 fifths. Oh, that's going to be 5. All right, and then we have 10 divided by 2 is going to be 5, and then 50 divided by 10 is 5. So I have a common ratio. All right, so y, and then y, because I have a common ratio of 5. I tried subtraction, and it just wasn't going to work. And then I tried division. All right, I divided 2 by 2 fifths, 10 by 2, and 50 by 10. I got the same common ratio for all of them. So it gives me a geometric sequence. Now, what is the explicit formula? So we talk about exponential function, which is geometric. and we need the explicit formula for that. Well, again, go back to your 7.2, go look at your notes, have this formula ready, easily available to you, and ready to rock. So we have A1 plus, oh, I did that wrong. See, this is why I got to have it written down, times R n minus 1. All right, well, A1 is my first term. What's my first term? Is it 1? No, it is 2/5. This tells me which term it is. This is my first term, so my first term is 2/5. My common ratio is 5, because I'm multiplying by 5. And then I'm n minus 1, and I'm done. That's it. All right, so that's all we needed to do. Did I make a mistake on question 6? I think I did. I think I did it right. Maybe they did explicit formula. All right, and then question 8. We did fine. All right, that's all good. Sorry, my notes are telling me that question 6 is wrong, but it looks like they did the explicit formula, not recursive. Yeah, it's explicit. We good. All right, so now we need to know what linear. All right, so I'm gonna cover this a little bit. So we have linear increasing, linear decreasing, and then we have exponential growth and exponential decay. Okay, so linear increasing and linear decreasing are arithmetic sequences. All right, so they're arithmetic sequences. That's what they are. So anytime you have linear or anytime you have arithmetic, it's going to be a straight line, which would be number 9, linear increasing. All right, it is a arithmetic sequence, right? And it is going up. So this is linear increasing because I read it left to right. Another way, if I was given a table of values, for me to have linear increasing would need to have a common difference that's positive. All right, and that's it. The common difference tells you it's arithmetic. The positive tells you it's increasing. That's linear increasing. If you wanted decreasing, if you wanted linear decreasing, you would need to have a common difference, right? This is if we're given a table, that's negative. And that would be going down. All right. Now let's go to the exponential. Exponential is geometric. All right. Exponential is geometric. All right. Now left to right, this is decreasing. This is exponential decay. All right. Now, what you're looking for here for decay is, let's just, I think I have a better idea just to show this point. All right, so let's give me a recursive formula. So we'll start 7 times 4 raised to the n minus 1. All right, so in this scenario, my common ratio is 4, right? So I have a positive common ratio greater than 1, and this is an increasing function. If I change this 4 to 1 divided by 4, notice how it now is decreasing. So if I have a number that is greater than 1, I have an increasing geometric sequence. And if I have a function that is less than 1, like a fraction, greater than 0 but less than 1, I have a decreasing. What happens if I make this negative? It goes down. It just flips, right? So all the negative does is flip you over the y or the x-axis. All right, so if I do the same thing for here, and I want to come there and make this negative. Oh, am I naming? See, I'm not even show. So a negative fraction isn't even going to work. It looks like. Cool. So 4 For exponential growth and exponential decay, what you're looking for. So for decay, you're looking for a common ratio that is greater than 0 but less than 1. For growth, you want a common ratio greater than 1. If you make it negative, it flips over the x-axis.